So the question is, G is a reductive algebraic group. Acting on a projective variety X and linearly. And let me recall what the, sorry? Characteristic 0, algebraically closed field of characteristic 0. Let's say over C. This would be good. This is unstable if so this is an affine point over X, and if this contains the origin, the orbit closure contains the origin, then it's called unstable. And the numerical criterion says that it is unstable if there is a torus, let's say maximal, such that the T orbit contains the origin. Yeah, linearly, yes. With respect to this embedding, so it factors through this. Now, so my question is, how hard, given an unstable, let's assume that a point is unstable, how hard is it to find destabilizing T? So I asked this question to many experts, and I got really all kinds of answers. And some said that if it's unstable, then you can choose any torus, and probably you will find the destabilizing one parameter subgroup. And others said that, well, there might be some strange counterexamples, and so on. And I've submitted this in two separate papers, one on semi-simple case and the other in reductive groups with non-trivial radical. And there were two kinds of referees as well. One of them, which I call the good referees, thought that this is a really interesting problem and a fundamental result which should be interesting to lots of people. And the other referees, which I call the regular referees, and they were not as impressed. Anyway, so the theorem that I'm going to give you is well, before I give you the theorem, I think I'll give you one example, or maybe two. So one stupid example is hyperplanes. So hyperplanes in Pn, of course, you can write it as AIXI is 0, and that's going to correspond to this point in the dual. And to, that's a nice safe. And to destabilize this hyperplane, you change the coordinates so that it becomes x0 equals 0. So you make this simple coordinate change. And you take this one parameter subgroup, T and T inverse 1, 1, 1. And you take limit of lambda of t dot that point which is 1, 0, and that's 0. So, well, this is a stupid example, but you see that even in this example, you have to make the right coordinate change to destabilize it. Yes, so how hard is it to find a T which contains a destabilizing one parameter subgroup would be a more precise question. Yes, but well, if you if you find one parameter subgroup, it will be contained in a maximal torus. Right? So in practice, you choose a coordinate system, and then you find the one parameter subgroup. Now, so anyhow, so if you make a generic coordinate change, then all of these coordinates will not be 0. So you see that that point is going to be T stable in generic coordinates. So generic coordinates is the same thing as in general torus T. This point is going to be, none of these will be 0. So is T stable. The next question is hypersurface. And this is where, this is the only place where the word the surface comes up in my talk, unfortunately. Now, hypersurface. So in this case, the group is SLN plus 1 acting on the hypersurface of degree D, and it's this representation. And this is, you pick a coordinate, say x0 to xn, and a point in that representation is a polynomial C alpha, X alpha. I'm going to use the multi-vector notation xi to the alpha I. And I claim that this is always semi-stable in generic coordinates. So let me define the state polytope and generic semi-stability first, before I prove that that point is semi-stable. So as before, let G be a reductive group and V is a rational representation. And let's pick a maximal torus and pick a point V. Then the state, this is the state, is defined to be chi in x of t, character such that V chi is not 0. And state polytope is simply the convex hull of this guy. The convex hull of in and V is T semi-stable if and only if this convex polytope contains the origin. Origin is the trivial character. So in this case, these monomials can be thought of as the character. Right? This forms a basis of this particular representation. And if you take the maximal torus consisting of elements diagonalized by x0 through xn, then let's say this whole thing is V, and V is C dot x alpha, and these are precisely the weight spaces. These are the weight spaces. I'm sorry, I should have given you the definition of generic semistability. And B is, this is terrible, generically semi-stable if there is a non-empty open U such that PV of GTG inverse. So here I fix the maximal torus T, and all maximal tori are conjugates. So I only need to look at these guys, and if the state polytope with respect to GTG inverse contains the origin for all G in U, then we say that this is generically semi-stable. So what this is saying is that with respect to a general maximal torus, this point is semi-stable. And this statement is the same as P G dot V of T contains the origin. Because you can either move the point or you can change the coordinate system. So if this containing the origin is the same thing as the point moved by the G action containing the origin. Sorry? Yeah, it's even less than that. So I'm either moving the coordinates. It's the same thing as moving the point. So it's same thing written in different ways, in two different ways. All right. So here, time flies. But So here's a proof. One proof that I will do in this talk is that in hypersurface is always generically semi-stable. Generically semi-stable. So if you look at the G action on one monomial, then this is going to be product of G ij xj to the alpha, right? So if you look at G dot F, then this is C alpha G dot X alpha. And after you do the action on the monomial, then this is going to be some sort of function on G, and say C beta and X beta. And the important thing is that if you write down C beta, right? So I'm going to write this as C alpha beta of G X beta. And if you look at this function, then this is multi-homogeneous of multi-degree alpha 0 through alpha n on these variables, G01, G0n. So you've got this n plus 1 sets of variables, and this coefficient is going to be multi-homogeneous, multi-degree alpha 0 through alpha n in these sets of coordinates. So if you you take f equals a alpha x alpha and take the G action, then you're going to get a alpha C alpha beta of G x to the beta. And the observation is that if you take this summation over alpha, this is never 0. This is never entirely 0 because all these functions have different multi-degree. Since C alpha beta G have different multi-degree, this is never 0. It's not non-vanishing, but this is never entirely 0. So what you do is you take U alpha to be G such that A alpha C alpha beta G is not 0. And you take the intersection. And if you pick an element G in here, then G dot F will have all monomials. All monomials appearing in the expression. Therefore, the state polytope will obviously contain the origin. Yes. Right. Yes. So here it's semi-simple. I hope I was. Right. So here I'm looking at the semi-simple case. Okay. Takes a lot more time. So by a similar argument, you can think of this case SLN plus 1 acting on L symmetric power of, say, MCM plus 1. So this is a Hilbert point case. Right? You have an ideal generated by L degree m monomials, and that's going to define a point in here. And you let SLN plus 1 act on this representation. Then by a similar argument, you can show that Hilbert points are always generically stable. So stable means that the origin is not just contained in the state polytope, but it is contained in the interior of the state polytope. So 0 is contained in P V of the interior of this state polytope. The theorem with Park is, in fact, if G is a semi-simple algebraic group and V is any non-zero point, is generically semi-stable. So even in a worst, really terrible or simplest GIT problem, you have to choose a maximal torus carefully to destabilize an unstable point. So that's the nutshell of this theorem. And the proof is, again, quite similar to what I've done in this hypersurface case. So the proof really follows from the fact that the Weyl group acts on the set of weights of this representation, and the Weyl group acts transitively on the set of Weyl chambers. So if there is one character, one state, then you move it around by the Weyl group action, then the convex hull has to contain the origin. That's the proof. So now, the question that I've been interested in for the past couple of weeks is, then when is V in V generically stable? So my theorem with Park guarantees that any point is always generically semi-stable. So when can you say that the point is generically stable? The trivial character is contained in the interior of the generic state polytope. So if you look at the Hilbert point case, the Hilbert points are always generically stable because SLN plus 1, because of the SLN plus 1 is almost simple. Hilbert points are not just generically semi-stable, but they are generically stable because SLN plus 1 is, SLN is almost simple. Almost simple means that there are only finite groups. It contains only finite groups as the proper normal subgroup. So if you know that SLN mod mu n is PSLN, and this is simple. It has no proper normal subgroup. Therefore, this is the reason why Hilbert points have are generically stable. So let me recall some basic facts about semi-simple groups. Recall that G is a semi-simple if and only if G is product of almost direct products of its almost simple subgroups. So you have this sequence. It's a finite subgroup, finite kernel, and you've got these G1 cross GR. These are the almost simple subgroups of G, and you have the product map to G. So this exact sequence means they're almost simple. It's what it means to say that it's an almost direct product of almost simple subgroups. So suppose a simple factor. So these GIs are called simple factors of the semi-simple group G. And if a simple factor GI is contained in GV, so if a simple factor fixes the point in question, then obviously then the state is contained in a proper hyperplane. Defined by phi upper star is 0. So what's phi upper star? So you've got T. T is almost a direct product of Ti in Gi. So you've got Ti going into T, and this induces the map X of T character groups to just a pullback X of Ti. So just because Ti has to act trivially on V, any state of V with respect to T will satisfy this equation. So this means that if the state is contained in the hyperplane, therefore state polytope is going to be contained in a proper hyperplane. Therefore, it has no interior. So this implies that the state polytope has no interior. And this is the only case where a point fails to be generically stable. There's the theorem. So it's in fact pointed out to me by a referee. V is generically strictly semi-stable. If and only if a simple factor of G acts trivially on V. So this is the end for the semi-simple case. If you have a semi-simple algebraic group and a rational representation, then every point is generically semi-stable, and it is strictly semi-stable if and only if a simple factor acts trivially on V. And you can easily generalize this to reductive groups with a non-trivial radical. So let me just jot down the theorem first. The theorem is, this is going to work with Donghoon Bak. And G is reductive. And V is a rational representation. Then V in V is generically semi-stable if and only if V is semi-stable with respect to the action of the center. The radical action. So this is the radical. Radical of G. So in the reductive case, the radical equals the central, the identity component of the center. So it's a central split torus. Now, an expert in algebraic groups will see this and probably think that this is very trivial. And it might be so, because if you know that reductive G is an almost direct product of the radical and the semi-simple part. So which is derived. This is G prime is a semi-simple. And this is a central torus. So you have this exact sequence. 1 goes to RG meeting G prime. This is finite. And torus cross G prime and G to 1. So you see that there's not too much difference between G and the torus times the semi-simple. Therefore, you can even naively guess that we have already proven that any point is generically semi-stable with respect to this semi-simple part. Therefore, you can guess that, oh, well, if a point is semi-stable with respect to the other factor, then it should be semi-stable. But I'll show you this example that it's not that straightforward. It's pretty easy. I'm the first to admit that it's not a deep theorem. But see, if I take C star cross C star acting on C2, GL2, let's say this is the first torus and this is second torus. The T2 maps to S inverse T and S inverse S and T S T and T inverse, right? S squared maybe. So ST, the first torus S goes into S inverse S squared, and the T goes to T and T inverse. And if you take the point V in 1, 1, then obviously it has one positive weight and one negative weight. Therefore, it's semi-stable. It's actually stable. And here, both negative and positive weights are there. Therefore, this is stable with respect to both factors T1 and T2. But it does not guarantee that it is stable with respect to the product. Because if I take the following co-character, say tau is tau, I'm going to take T and T squared, is it? T squared and T cubed, right? And this is going to be T and T, right? So this is going to destabilize this V. Therefore, semistability with respect to each factor does not imply semistability with respect to the product. So you have to do a little bit more work. And it's not even the product. It's an almost direct product. So the analysis is just only slightly more involved. So you take the sketch of the proof is that you take a maximum torus and you can write it as an almost direct product of the radical and a maximal torus of G prime. Right? So this is a maximal torus of G prime, and this is the radical. Then what you see is you've got this almost direct product structure coming from the almost direct product structure of G itself. Then this maps induces x of t going into the character group of the radical and the character group of the torus of the semi-simple parts. And if you look at the root system, phi, you will see that phi goes into 0 and phi prime. The key point for proving this theorem is the Schur's lemma. Which says that you first look at the weight space decomposition with respect to the radical. So V is zeta in character of the radical and V zeta. It's a central torus, so you've got this weight space decomposition. And Schur's lemma says that, well, the simple computation says that this is a G prime module. Or actually G module. So you can further split this V zeta into a weight space decomposition. So you have zeta, and you can take chi prime in character group of T prime and V zeta chi prime. So once you realize that V can be decomposed into the weight spaces of this type, then you can easily figure out what the relation between the states with respect to T and states with respect to T prime. Then you can prove the theorem about the reductive groups with non-trivial radical. So from this weight space decomposition, you see that the state with respect to T, so let me name this function iota. It's identified with zeta and chi prime, such that chi prime is, in fact, in the state with respect to V zeta of R. I'm sorry, T prime. So once you have this relation between the state of V with respect to T and state of V with respect to T prime, then you can prove that zero is contained in PVT if and only if zero is contained in Let me just say this is general torus. Well, thank you for your attention. Mm-hmm. Mm-hmm. Small, yeah. Mm-hmm. Mm-hmm. Yes. Mhm. Yes. Uh, yes. So I'm afraid that this question of generic semi-stability, in my point of view, is purely of theoretical interest. So because once you have to do the actual GIT, then you have to use the geometry of the problem in hand to find one parameter subgroup that destabilizes your point in question. Although I'm not sure, but it probably does not have too much relation to Frank Cohen's work. Thank you.